see though, more or less? Okay, we'll play with the lights a bit more later. Okay, so yeah, we're going to be looking at the ARRI SkyPanel. The things we're going to cover today, hopefully, as long as we don't run out of time, is a bit of the science and technology behind it, as well as the lights themselves. So we're going to look at light, color temperature, different light sources and comparing them, quality of light, and then we'll look at a few different lighting fixtures and what the different types are. I mean, everybody's seen a prism before. When we are referring to a white light, we're actually talking about a spectrum, a full spectrum of actually all of the colors and frequencies of light. And this is important when it comes to certain types of lighting, which can be missing, actually, some of the colors from the spectrum. And we're going to look at that a little bit later and the implications of that on the quality of color rendering. So light is electromagnetic radiation. So it's the same spectrum as radio waves, AM, FM radio in your car, microwaves that you might use to heat your food, infrared, then we have the visible spectrum, ultraviolet, X-rays, and then gamma rays. So the light that you see, that we light our scenes with, that's coming down from the sun, it's all electromagnetic radiation. So when we're talking about visible spectrum, we're talking about between 400 and 700 nanometer wavelength. So that's our near ultraviolet through to deep red and near infrared. So that's the spectrum that we can see, and that's the spectrum that is important to us when it comes to... No, welcome. Yeah. Make yourself at home. We've got a few people, I think. Hello. Just send this to someone else in when they come. Welcome, guys. Just pick a seat. Anyway. Okay, so yeah, some of this stuff you may already know, maybe you don't, but it's all important background knowledge. So when we're talking about lighting for anything really, but for film, for TV, for cinema, we're talking about the visible spectrum. When we're talking about white light, we're talking about needing a full coverage of the spectrum to create our white light. So just looking a bit at color temperature, because this is one of the most important things that we talk about when we look at different lighting sources and when we look at planning lighting, is color temperature. So we're looking at, a white light can be warm and it can be cool. Is everybody's familiar with color temperature in terms of degrees Kelvin? And okay, so we're going to look at why do we have this color temperature? Where does this come from? So basically, color temperature is the color of white light which is emitted from what's called a perfect black body. So a perfect black body is any material or any body which radiates light perfectly. So that could be the sun. In this sense, it could be a metal. So we talk about tungsten as being a perfect black body radiator. And when we heat up a piece of tungsten steel, it starts to glow. And depending on the physical temperature, which we can measure in degrees Kelvin, or you could measure in degrees centigrade if you wanted. As you know, you've all seen hot metal before. The color that the metal glows changes depending on the temperature of the metal. The hotter the metal, the whiter the color is. The cooler this principle is the spectrum of our Kelvin-based color temperature that we measure all our lights with. So, anybody seen one of these charts before? This is called Chromaticity Graph. The whole graph on its own is actually called the CIE 1931 Chromaticity Chart. It was put together back in 1931, funnily enough, and it represents the whole graph as a whole represents the limits in terms of color or hue and saturation that human eyes are capable of seeing. So you might have seen it if you know anything about digital color science, when we talk about color spaces, in terms of even how we handle color in post-production and things like that, you end up looking at the same graph basically when we start looking at different color spaces. But it's a chart which encompasses all of the hues, saturation, colors that the human eye is capable of seeing. So the numbers we have around the outside, from 380 up to 700, corresponds to actually the frequencies of light back here, 400 to 700. So all of the colors that we're looking at here in the full visible spectrum, we're plotting around the outsides of this chart. In the middle of this chart is going to be what we refer to as a white point, or an exact, perfect mix of all the colors that are around the outside. And if we are to plot a line which represents our Kelvin color temperature, this is what the line looks like. So when it's put on a full chromaticity graph, including all of the other colors. So this line basically represents our standard Kelvin color temperature that we all talk about when we look at lighting. So degrees Kelvin are marked here, so 1500 to 2000 to 2500 all the way up to 10,000. So you can see that our color temperature goes from a deep orange up to where we normally consider tungsten balanced is up here somewhere. What we normally consider daylight balanced is 5600, that's over here somewhere. And you increase the color temperature even more, you go even more in towards the blue. And again, you can think of this line as representing even exactly the colors that you're going to get from that piece of metal that I showed a picture of as you heat it up. It's this line. And yeah. Does that make sense so far?
Yeah, sure.
Has everybody put these pieces together? Because I know when I first learned this stuff, it was a moment where a few disconnected things that I had known came together and I started to see a whole picture of how this all relates. Anyway, I'm trying to communicate that. So, okay, so correlated color temperature, CCT. You'll often see CCT, and it stands for correlated color temperature. What does that mean? Correlated color temperature just means it's a color which we perceive to be equal to or the same as a certain Kelvin-based color temperature. So again, just reinforcing, we've got Kelvin and we've got various different color temperature points here. So we're going from a warm through to a neutral through to a blue. So just quickly looking at, is everybody happy with color temperature so far? I'm not going to get any more scientific into that. Just that's what we're talking about when we're looking at color temperature. Okay, so in terms, one of the most important things that we need to look at when we look at lighting for film, for cinema, for TV is the color accuracy of the light source. And when we're talking about color accuracy, we're talking about looking again at that spectrum, full spectrum of colors that make up white light. We're looking at how full is that spectrum. Are we missing any wavelengths? Are we missing any colors of light within that spectrum? Because our eyes are our brain is very good at compensating. So we can see a light, maybe a fluorescent light fixture for instance, it looks white to us. Because our brain adjusts, our eyes adjust, it looks white. But the camera doesn't necessarily see it as white, because the camera sees that it has a big green spike in it. our eyes don't necessarily catch that. When you look at your image on a monitor, you start to see a green cast, you know, in what you're shooting, and that's one of the downsides of fluorescent lighting. So we're going to get into that a little bit more. But when it comes to measuring or, you know, quantifying the quality of the accuracy, the color rendering accuracy, we've got a few terms that get thrown around a lot. Has everybody heard of CRI? Okay, CRI is actually a fairly inaccurate measurement, but it's one that gets used a lot. So we've got CRI and we've got TLCI. These are two kind of measurement systems that you'll come across quite often whenever you're looking at any lighting source, but typically LEDs and fluorescence even as well. When we're looking at daylight, when we're looking at the sun, or when we're looking at a tungsten light source, for instance, we have what we consider pretty much perfect color accuracy. But when we look at some other artificial light sources, like LEDs or fluorescence or whatever, sometimes there can be some issues. So the CRI and TLCI are all measures of color rendition accuracy. So CRI stands for Color Rendering Index, and TLCI stands for Television Lighting Consistency Index. Okay, so these are two important things to see, and you will notice these whenever you look at specification sheets in terms of lighting from, not just from ARRI, but from any manufacturer actually. So some of them only give CRI. What you want to really look for is the TLCI. So we're getting into a little bit of what the differences between these and what these are. So CRI. The CRI is calculated by comparing the appearance of a range of sample colors when observed under a perfect light source, which is like daylight or tungsten, or a standardized artificial source like tungsten, against whatever light that we're testing. So it's an A/B test. We look at pure daylight or a tungsten light source and a range of colors as they appear under that light source, and then the same range of colors as they appear under our whatever it is that we're testing. So it could be an LED light, it could be a fluorescent light, whatever. We compare the two. So the results across the sample colors are averaged out to give a single score. So with 100 being given to a light which renders colors as accurately as the standardized source. So that means a CRI of 100 means that light is as perfect as daylight sunshine outside, or as perfect as a tungsten light source, which doesn't really exist. So none of the LEDs or fluorescent lights or anything get a CRI of 100, but we get close. So yeah, to ensure accurate color rendition for filmmaking, especially with skin tones, is really where this is important. If CRI is the only number that you see, or the only number you're given, and then there isn't TLCI, which we'll come to in a second, you're looking for a CRI of between 90 to 95 or higher, is really what you want to be looking at for any artificial light source to give good quality colors, and especially when it comes to skin tones. So we'll take a quick look at TLCI. TLCI now is a similar type of measurement, similar type of comparison, but there's a key difference. So the process to calculate the TLCI for a light is similar to that for CRI, in that, again, it's a set of color samples compared under a standardized perfect light source, and then whatever light you're testing. But the key difference here is rather using, I don't want to make it sound like our eyesight is bad or there's anything wrong with our eyesight, but it's subjective, it's not objective. So rather than using a human observer or what the comparison looks like to our own eyes, we use a camera basically and software to calculate the differences. So it's a lot more accurate because, like I mentioned already, our eyes and our brain can be very forgiving. The camera tends to be not forgiving at all. So CRI, is something that is more a measurement based on human perception. TLCI is a measurement that's based on software and on a camera. So wherever you can find TLCI, that's the more accurate measurement. So again, same kind of thing. It also produces a single average score up to 100, so it's 0 to 100. Scores in the range of 85 to 100 would need not really any color correction. 70 to 85 would be pretty simple to correct, but 50 to 70 indicate your footage would need complex color correction post. But any of the lights that you're really looking at, I mean, not to mention the lights that are here that we're talking about today, but pretty much any of the lights are going to fall between 70 to 100. A lot of them are in the low 90s. So yeah. Any questions on CRI or TLCI? Does that make sense now? So when you're looking at lighting spec sheets and you see TLCI, a little number, now you know what that means. Basically, just remember, the higher the number, the better. That's what you need to remember. The higher the number, the more accurate your colors are going to be on your footage. So, this brings us to our main problem, really, which is what I've referred to as a broken spectrum. So, daylight, so that's light from the sun, or it could even be light from the moon for that matter. But daylight and artificial lights, such as tungsten filament bulbs especially, are what we consider full spectrum light sources. Okay, so what that means is, when I showed the slide at the beginning of white light going through that prism and it breaks it down into a rainbow, that rainbow is a full spectrum. It's everything from violet all the way to red, and there's nothing missing. So that's sunlight will do that, and light from a tungsten filament bulb. It's kind of, no worries, the kind of old school bulbs that, actually I don't even mention buy them anymore, but we're replacing them all now.
Excuse me.
Yeah. That's TLCI and CRI are talking about white light. When we're talking about white, it's white somewhere along that line of color temperature. So it could be anything from 2,000 Kelvin up to 10,000 Kelvin. But along that line, in terms of color temperature, that's where we're talking about TLCI and CRI. Because obviously a light that's this color is not giving out the full spectrum. That's why it looks red or pink. So yeah, we're talking about white light sources. So though the intensity of light may vary between the red and the blue ends of the spectrum, we're going to look at some more charts in there. It's unbroken. So that means even though a light may have more red in it than blue, traditionally, well, still with fluorescence, with LEDs we've got some solutions which we're going to come to. But fluorescence and LED light sources produce a discontinuous spectrum consisting of only certain colors. So part of the problem with LED lighting, and still a problem with fluorescent lighting, is that LEDs typically don't produce a full spectrum of white light. They produce a very narrow band, single frequency of light. One way that I kind of try to explain this is, it depends on the color of your object. Like, an object appears to be a color because it's reflecting that wavelength and absorbing all the others. So a red apple outside under the sun, it looks red because it's only reflecting the red part of that full spectrum of light. All the other colors in the spectrum, it's absorbing, it's reflecting red. That's bouncing into your retina, and that's why it looks red. Same with everything of any color. But if you've got a light source which is missing red, and you've got a red apple there, it's not going to look the right color red. It's going to look kind of, actually if that particular color is missing, it's actually going to end up looking very dark. And that's kind of what happens of daylight. So you can see here we've got a very full spectrum. That's why daylight is the best, really it's the nicest light to shoot under. It's because it's a full spectrum. And as I was saying before, even though the intensity, which we have here in terms of how high the graph is, even though the intensity of the different colors in the spectrum might differ, it's still a full spectrum. It's all there. It's not broken. That's the important thing. So sunlight is always, our gold standard. The other gold standard that we compare everything to is, anybody guess? Tungsten. Yes. So our two standards are daylight and tungsten. And the reason they are standards is not just because they are arbitrary numbers that the industry adopted. And so 3200K and 5600K are magical, standards. It's because of the quality of light in terms of the spectrum you get from daylight and from tungsten light. So we can see here incandescent, tungsten incandescent. Incandescent just means glowing. So it comes from, the fact that we've got a tungsten steel filament inside a bowl, which is heated up by the current flowing through it. And it's incandescent, it's glowing. So incandescent tungsten, you can see we've got again, even though the intensity tapers up from not much on the blue side to a lot on the red side, it's a full consistent spectrum. We have everything. So the amount of everything differs, but we have everything in the spectrum. So can you see, comparing incandescent and daylight, where the differences in color are happening? So daylight appears more blue because we've got a lot more happening on this end of the spectrum in terms of intensity, and we've got less on this end of the spectrum. Tungsten looks warmer, or more of a gold, yellow color, because intensity-wise, you can see we've got a lot more happening over here than we do over here. So that affects its color. So that's why our tungsten lights are a very warm light, because all the action's happening over here on the warm end of the spectrum. But we actually do have everything. It's just the intensities are not all the same. Let's take a look here at CFL, which is our fluorescent. Can you see here why fluorescent is such a pain? It's got spikes and dips all over the place. So with fluorescent lights, we've got, it appears white because we have, it appears white to us, to our eyes and to our brain, because we have a strong blue component, we have a strong green component, and we have a strong, well, it's red, but it's actually kind of orange. And that gives us our red, green, and blue. That makes it look like white to us. But what the camera sees is that all of this in between is missing, or is very, very low in terms of intensity. So this chart here explains why our fluorescent lighting may look okay to our eyes, but to the camera, it's a mess. This chart is a mess. Okay, LEDs. This is an LED spectrum back here in the back. And it's a fairly good one. And you can see how it's a lot more similar to the incandescent. Apart from a spike in the blue, which there usually is on any manufacturer's LED lighting, it just depends. The intensity of the blue spike depends from it differs from manufacturer to manufacturer. But it usually doesn't really cause a problem. But we've got a general upward trend, missing a little bit on the red side. But this is a typical spectrum chart for an LED light source. But still, quality-wise, it's a lot closer to incandescent tungsten than it is to fluorescent. It doesn't, LED at least doesn't have the problems that are associated with fluorescent. And it's a nice full spectrum. We can do better than this. Even this is a typical LED graph, but ARRI, for instance, they even better this. So far, is that making sense? Yes? No? To some people? Okay. Anyway, it's important to know this stuff because then when you're looking at lighting and when you're making decisions for yourself, you're making informed decisions knowing wavelength in nanometers on the line, so we're again 400 to 700. Any questions so far?
I have a question about just relevant.
That's fine.
This section, why LED is so painful to make, and why what's the cheap one?
Yeah, I'm going to get into that. The thing is, LEDs are complicated because, for some reasons I'm going to get into, because of how they work, and because of how they produce light, and because some of the workarounds that have to be done to get a full spectrum light out of LEDs. So I think we're going to look at that next, as the next thing. So old school LEDs that you're used to seeing kind of look like these. Everybody's seen these? Some of the first LED panels that came out, you know, it was a one foot panel filled with little white LEDs. Okay. The LEDs we use now don't look like this anymore. They look more like this. They're surface mount LEDs, and they operate on a slightly different principle. And I'm going to get into that. It involves phosphor and stuff like that, which we'll get into. But anyway. The LEDs we use now are a lot more accurate, they look a lot more like this. So, first of all, what is an LED? An LED is a light emitting diode. So it's a solid state device, like a computer chip, like a computer memory chip. You know, it's not a little piece of metal which gets hot. It's a solid state device which emits light of a frequency or a color equal to what we refer to as the band gap of the semiconductor use. Now, you don't all have to become physicists, so we're not going to get into to that, but it basically it has to do with how electrons move from hole to hole inside of a semiconductor. The band gap between that is a physical distance in nanometers. So if you had a tiny, tiny, tiny enough ruler, you could actually measure it. It's a distance, and that distance is in nanometers is equal to the color of the light in terms of the frequency of the light. So you remember how we talked about the spectrum of light, the colors being between 400 and 700 nanometers? When we talk about a nanometer, it's a physical distance, like a mile or a kilometer. It's just really, 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 really small. So the thing about LEDs, they emit a single narrowband frequency of light. So that means a red LED emits red light. A blue LED emits blue light. It doesn't emit that full spectrum. If you were to go to an electronics supply store and look at LEDs, the color of an LED would be given in nanometers. It would have a very specific frequency, a very specific color. So if we were to make a chart, spectrum chart, of the light coming off of one of those LEDs, it would just be a massive peak. That's all it would be. So on its own, it's not very well suited to, to the kind of light we need. But here's where things get clever. Does everybody? You're all old enough to remember the first LEDs that started to come out were red. Everybody remember that? The first LEDs that you ever started to see, they were red. And they were on like digital alarm clocks. You know, have you ever seen those big old school digital alarm clocks that sit by your bedside? You got those, you know, the segmented display. Yeah, calculators. So the first LEDs we had, and we're talking back in the 70s now even, they were red. They were the first ones to make, they were the easiest ones to make. Then we started to get like orange LEDs, even green LEDs into the 90s. And by the late 90s, we started to get the first blue LEDs. Blue was the hardest color to make an LED give off blue light. But once we had blue LEDs, then we had red, we had green, we had blue, and we could start making white light from LEDs. But there's a better way. The better way is using phosphor coatings, and that's what we do now. So phosphor coatings allow white light to be emitted as a full spectrum mixture of red, green, and blue by using different phosphors. So phosphor is it's a coating which takes a certain frequency of light and absorbs it and emits all kinds of other frequencies of light. Basically, that's what a phosphor does. So phosphor coatings, basically they fluoresce and they emit a full spectrum when they're excited by blue and near ultraviolet LEDs. So the fact that we can make blue LEDs now and even near ultraviolet LEDs means we can make light which excites a phosphor coating, and that phosphor coating emits a full spectrum white light. So now all of a sudden, because these technologies have kind of lined up, we can make a full spectrum white light using LEDs. And this is a remote phosphor LED light. This is the S60 RP, and you can see the little LED surface mount LED panels in there. These actually emit a blue, almost an ultraviolet light. So if we were to turn it on now, well, actually it doesn't turn on if this is not in. But this is the remote. This is the phosphor panel. So it looks yellow, but it's actually a phosphor coating. So the LEDs in here are actually, if they were on, they would be almost like a black light. If you've ever been to a club with a black light, it makes everything white glow. It's a very, very purpley blue light. But as soon as we put in the phosphor panel, that blue light excites the phosphor in this panel, and we get all of a sudden a full spectrum white with, if we were to break it down in a chart, it would be a nice full spectrum white light from an LED source. So whenever you look at lights that say that they are remote phosphor, they're remote phosphor because the phosphor panel is separate from the LEDs. We're going to look at this a little bit more. Sometimes the phosphor is not a separate panel, like on this light, but it's actually, the phosphor is part of the LED. It's on the same chip as the LED. That's the other way of doing it.
Excuse me. Does it get, the phosphor, does it get warmer?
No, it doesn't affect the temperature at all. The RP lights, the remote phosphor lights, they come in two models, the S60 and the smaller size S30. They actually produce a slightly more accurate color white light than the C versions, but it's almost immeasurable. But it is slightly, RP is slightly more accurate color-wise, and it's also slightly more intense. So there's a slight brightness difference between the RP and the C. The RP is a little bit brighter. So does that make sense so far? Okay, we're going to move on there. So advantages and disadvantages. Also, just so you know, different types of phosphor fluoresce with different spectrum of light. So the red, green, and blue lights that make up our C versions of the lights, which are the ones that can do any color. The phosphor is on the LED itself, and the different phosphors make red, green, and blue. But they make red with a very full spectrum red, and green with a very full spectrum green, and blue with a very full spectrum blue. So any one of those LEDs is not the full white, but together they make a very full white spectrum, and they can be tuned all the colors of the rainbow because they are separated red, green, and blue. Whereas with the remote phosphor, we can't do all those colors because the phosphor panel is just giving us that white light. So, advantages and disadvantages when it comes to LED lighting compared to other types of lighting. LED lighting is incredibly efficient. So the amount of light that you get out for the amount of electrical power you put in pretty much beats anything else. HMIs, funnily enough, actually are also quite efficient, but they're very hot and they use a lot of power. But LEDs have a very high efficiency. Very low power consumption. disassemble and move the light fixture. You know, people can get burned very easily. You know, you melt through your gels. Has anybody melted through their gels before? That happens. They're very hot lights. LEDs, on the other hand, are very cool lights, temperature-wise. Compact. So LEDs panels tend to be very small for their light output, and they tend to be quite lightweight. So lightweight. Color rendering is very high. So if you go back to what I was saying about our standards for the highest color rendering quality being daylight and tungsten lighting, incandescent tungsten light bulbs, LED would be the next, in terms of the technology used in these lights, would be the next quality in terms of color rendering. So for something that is not daylight and not incandescent tungsten, LED has very high color rendering in terms of this technology. And cost as well. So disadvantages, really one of the only disadvantages of LED lighting in general at the moment is that they still have relatively low total power output. So LED lighting is getting more and more powerful in terms of punch, in terms of light output. But when you're in a situation when you need really, really bright light sources, LEDs are still, technology-wise, I'm not going to cut it yet, you're still going to need to be looking at HMIs and things when you need a huge amount of punch. But they're getting brighter all the time. So we looked at this. I just wanted to put up a kind of a, just check the time because we want to have a break at some point. Okay. We'll have a quick break after this, I think. So just looking at remote phosphor again. This is what a remote phosphor, cutaway looks like. So if we were to slice through that at 60 RP and look at it sideways, this is what we'd see. We'd see LED chips, which are giving us a blue, almost ultraviolet light. We've got a reflective chamber, and we've got a remote phosphor panel. So we're getting blue light that's bouncing around inside. It's exciting the phosphorus in the remote panel, and we get a maximum full spectrum white light being released from the phosphor panel. So the light that we actually see is being emitted from the phosphor panel itself. Not from the LEDs behind it. The LEDs behind it, all of that energy is getting absorbed and re-emitted from the phosphor panel. So yeah, and the only difference between this, a remote phosphor, and the other LEDs is that if you imagine taking this phosphor panel that's on the front with the light off, making it a lot smaller, and fixing it onto the little LED chip itself, that's the technology that is used in the other lights as well. It's just that the phosphor, the type of phosphor gives off a red spectrum, a blue spectrum, or a green spectrum. It's still phosphor-based. So yeah, phosphor panel separate from the LED. That's what we're looking at. Phosphor panels are interchangeable. That's something I haven't mentioned yet, and nobody has asked about, which is in the case of the RP light. How do you change the color temperature? Because this panel only gives off a certain color temperature. So there is no knob to change the color temperature. You actually have to physically take the panel out and put in another panel with a different color temperature. So it's pretty easy. And after our break, we're going to look at the fixtures specifically, and you'll see the range of color temperatures that the phosphor panels that come from the RP. So they're interchangeable. Like I mentioned before, they do have slightly higher output than the full color models. They have a slightly higher color rendering quality. They are a little bit cheaper when you look at the cost of the RP versus the C versions. The RPs are a little bit, actually, they're quite a bit less cost. So if you don't need this is the part that I'm going to skip through a little bit quickly. But I'm happy to email you the PDF. So, yeah, open face spotlight. So, open face lighting fixture has no lens, so it doesn't really have a way to focus or control the beam. So, it can't be spotted or flooded. It's just an open face, harsh light source. But it does have its uses. It's a hard light. It's often used as a light source to bounce off walls or bounce off bounce boards or with diffusion. Can be used to light backgrounds, but it can create multiple shadows due to the type of reflector that's in an open face light. Fresnel spotlight, this is your typical, like what you normally think of when you imagine a cinema light or a film light, you think of a Fresnel light. It produces an attractive light quality and a very even field of light because of the Fresnel lens. It's a hard light again, so it's going to give you very hard edged shadows, not soft shadows. Can be used directly to light subjects if that's the look you're going for. Because the lens, the Fresnel lens, does even out the field of light. So an open face light, you're typically not going to point at somebody. You're going to point it at a wall or at a ceiling and you're going to bounce it off something. A Fresnel light, as long as it's not right in their eyes and going to blind them, you can light a subject directly with a Fresnel light, if that's the look you're going for. Or again, it can bounce off something, or you can use diffuse of different strengths. It can be used as a hard light for any purpose. It will give a single shadow due to the nature of the Fresnel lens. That's something you always want. That's actually a downside to some of the earlier LEDs as well. Some of the earlier LED panels, not from ARRI but from others, as well, would give you multiple shadows depending on how the LEDs were used. Because if you think about it, the older panels, the ones that you might recognize with those little LED lights themselves, like in an array, every single little LED is a little light source. So every one is going to produce its own shadow. And that's something that the sky panels from ARRI totally get around as well. But some of the earlier ones did that. So yeah, so a Fresnel spot gives you a single shadow. Beam can be focused, obviously, spot to flood. And then we've got soft light. So soft lights can be more forgiving on people generally. They produce a more pleasing rendition of skin tones. So again, like I said, your roll off between midtones and shadows and midtones and specular highlights is a lot smoother. So it looks nice on people. It's dispersed in many directions. That's one of the biggest differences. So the spots, whether it's a Fresnel or whether it's an open face, your light's coming out, straight in a very specific angle. With a soft light, because of the diffuser panel, it's dispersed in many directions. It bounces off of things. It produces a more full light. The downside of that is a soft light can be harder to control. There's various accessories, for instance, with the sky panels that allow you to control spill. Another thing I've mentioned here, spill light from diffuse sources has to be controlled. Everybody heard of like an egg crate? You know what an egg crate is? An egg crate is, I don't have one here, but an egg crate is it can be metal or cloth, really, and it clips on the front, and it looks like a grid, almost, the squares. Sorry? Like a honeycomb almost, yeah, but it's like square. Anyway, and it sits out, maybe this thick or so, it sits out from the light, and that stops, it blocks light from, it controls the angle, the maximum angle that light can come off. Anyway, it's a way of controlling spill. There's also what's called a snoot. A snoot is just a metal box which extends maybe a few centimeters out and again covers the edges. That's called a snoot. There's various different accessories that can be used. So now the bit that I really want to talk about until the end is the actual panels themselves. So, all that technical stuff is now done. So now we can look at the sky panels themselves. So we've got the S30 and the S60. These come in two versions. We've got C for color, RP. Anybody guess what RP is? Yes, remote phosphor. Very good. And much more recently, it was announced at IBC and revealed at IBC, which was a month ago now. We were both there. So yeah. In Amsterdam was the S120. So we're going to look at that as well. We've got all of them here. So the RPs have the yellow panels. So you can see the two different sizes, 30, 60, 120. The 120 only comes in a C version. There's not a remote phosphor version of the 120. The reason that we were given for that is that if they were to make a remote phosphor panel big enough for the 120, the phosphor panel itself would cost almost as much as the light. So they've not done a remote phosphor version of the big one, the 120. So yeah, the things you need to know are just C for color, RP for remote phosphor. So, and 30, 60, 120. The numbers really come from the size. So the S60s, it's 64.5 centimeters, but you can think of it as 60. Obviously the 120 is twice as much, so it's 1 meter, 1.2 meters. And the S30 is 30 centimeters. The width, well, the height, I guess, is always the same on all three models. It's always 30. So 30 by 30, 30 by 60, 30 by 120. So, and also the profile. The profile is just under 14 centimeters, and it's the same again through all three lights. So sizing-wise, they're the same. So yeah, we'll move on. So correlated color temperature. We're talking at the C now. So this is the S120C, the S60C, the S30C. The C, the color in many cases is the most interesting light because of all kinds of things you're going to find out. So the different modes that you've got CCT mode, which is correlated color temperature. So this is where the mode where you can dial in your exact color temperature from 2,800, say, or 2,000.
Sorry?
The color temperature range, 2,000
2,800 to
to 10,000. 2,800 to 10,000, that's in the CCT mode. In the CCT mode, you've also got your plus minus green. So that's obviously in terms of, if you think about the color wheel, in terms of color correction, opposite of green is, anybody? Magenta. Okay, so opposite of green is magenta. So if you were to think about your line of color temperature from 2,000 Kelvin to, or 2,800 Kelvin to 10,000 Kelvin, then above and below that, you've got an adjustment for a little bit of plus or minus green, which is green or magenta. That's in CCT mode. Vivid color mode is what we've got here. I sometimes refer to it as disco mode because it's kind of fun. So you can really, there's various ways that you can plot the color in vivid color mode. On the control panel, it gives you three little letters called HSI for that mode. So that's hue, saturation, and intensity. So not in this mode now, it's got a straw on it, but if we go back. Okay, afterwards you'll have to come up quickly and have a look before everybody disappears. But if you were to have a look at the back, it says HSI. Hue, saturation, and intensity. So I can change the hue, I can change the saturation. That's zero saturation, which basically just means it's white. But again, as you increase saturation, it just increases that particular hue. And then you've got intensity, which is your output. So that's the vivid color mode, or the HSI mode. And then you've got a gel mode as well. So again, afterwards, come up, have a look, and you'll see that you've got a full intensity to 0. You've got a full gel library. So all the Roscoe and Lee filled gels, you know, the transparent plastics that you would normally put over a light. You don't have to pull them out and cut them and pin them with little clothespins and everything that you normally have to do because it's all built in. And they're perfectly calibrated to the colors of gels. So as long as you know what the code or the name of the gel that you would want to use, it's in the database.
Excuse me. This phosphor reacting to the light. Huh?
Yes, in these ones, there's 3 types of LED. There's a red, a green, and a blue.
Yes, and you said that it is according to the nanometers.
Yes.
So will this affect the sensors in the camera when you change shutter speed or
No.
this difference in nanometers?
Well, these are, okay, the way these are controlled is what's called pulse width modulation, which means it is a very high frequency, like almost on-off or pulsing, but it's so high, it's beyond any camera sensor to pick it up. So there is no flicker. There's no flicker. Not even if you're shooting with a phantom camera. 2,000 frames a second, there's no flicker. So, yeah. But that's a good question, but no, they're completely flicker free. So, as we said, these are fully tunable from 2.8 to 10,000. Vibrant color selection. High color rendering, which means that whatever color your object is, whether it's an apple or a car or somebody's skin or whatever's in your scene, you're going to get that color recorded on camera because there's a full frequency of colors in the white light. Okay, we're talking about white now, not necessarily the colors. But, low power consumption, so on the S60 and the S120, you're looking at 420 watts about. That's the amount of power it's going to draw. So if you think about your typical, your vacuum cleaner is maybe 2,000 watts. A hair dryer can even be 2,000 watts. An iron can be 1,800 watts. So when you think 420 watts, it's not very much. So the great advantages of this is that when you're on location and you're using building like house power, you know, if you're using tungsten lights or some smaller HMIs, you've got to be constantly aware of how much power you're trying to pull if you don't have a generator. You know, you don't want to put more than 2,000 watts on a single circuit in a domestic power circuit, or you're going to start tripping circuit breakers. With these, you can plug in almost as many as you want within reason, even to domestic power, and you're not going to start tripping circuit breakers. With tungstens and HMIs, you're going to, you really need to be on a generator if they're big lights. So low power consumption. And for the power consumption, huge output. So we're looking at the S60 here, and also the S120. One thing that you should know is the 60 and the 120 actually have almost pretty much identical power output. So the S120 is bigger in aperture, but don't necessarily think of it as double the power. It's not.
And the weight as well.
Yes, the weight as well. So really what you're getting from the S120 is a larger, what we call aperture. You're getting the same amount of light as from the S60, but you're getting it over a larger area. That's the real advantage to the 120. And it doesn't weigh any more than the S60. So the S120 and the S60 in terms of weight and in terms of intensity are pretty much on par. They use the same power supply. It's just that you're getting a much larger aperture with the 120. With soft lights, a larger area of light is always an advantage. So yeah, so the S60 and the 120, they're at full power, they're brighter than a 2K tungsten soft light. I'm not talking about a 2K HMI here. A 2K HMI is a lot brighter than these, but a 2K tungsten, these are brighter than a 2K tungsten soft light. Fully dimmable from 0 to 100, and they're completely flicker free. Lightweight and compact, and they're built to last. They're ARRI, and ARRI makes things to last. That's not to say you want to abuse them and throw them around, but they're built to take, rental or on-set, use. They're built to be used. They give you a beautiful soft beam of light. The diffusion panels are interchangeable, so these are the diffusion panels. They come in 3 versions. You've got a light diffuser, a standard diffuser, and a heavy diffuser. And they slip in and out just like the remote phosphor panels. Wide range of accessories. So I've shown here the space light is one accessory. You can see the accessories. I don't have them in my presentation, but you can check them out on the ARRI website. And I think in your in your pack as well, you've got some stuff. But you've got this, like I mentioned, the snoot, the egg crates. Trying to think now. There's a whole bunch of different lighting modifiers and accessories in the different sizes. They're thin, so in terms of profile, you don't have to have the power supply mounted on the back of the light, but one of the accessories that's available is a bracket to mount the power supply. So you've got 2 options. You can mount it on the back, or you can have it unmounted and have it on wherever. Onboard battery connection, I don't have that to show you on any of these lights, but there is a V-mount or Anton Bauer gold mount battery plate. So that's a battery plate, actually, but what this is talking about now is there actually is an input, a standard 4-pin XLR input for a battery pack. So that's the other advantage, is that you've got a lot of light on the go, so you don't have to be tied to house power. So yeah, depending on whether you've got a separate battery pack or whether you want to use V-mounts or Anton Bauer mount batteries, there's an option. You can be out in the desert, you can be out in the woods, you can be out wherever you need to shoot, and as long as you've got battery power, you've got light.
Do you know how much roughly give us the type of battery, Anton Bauer battery?
How long it lasts? Depends on the capacity of the battery. And it also depends on how bright and the intensity that you're using it on as well. I mean, you can calculate it. 420 watts, and you're looking at watt hours typically of a battery. So, if it was, I don't know, you'd have to calculate it out. When we're finished here, come up and have a look. The control panel is really simple to use. There's 3 knobs and there's 4 buttons, and whatever appears on the LED next to the button, that's the button you press. So it's very, within 2 minutes you can have your head around controlling it. Onboard DMX in and out. So this means you can daisy chain DMX. With a third-party like wireless or Wi-Fi DMX control, you could even control these from an iPad or from an iPhone or whatever wirelessly, or any standard DMX controller. RDM implementation, which is remote device management. USB connection for firmware updates. That's the other thing we were just talking about at the break. It's a little bit kind of blows your mind, is that your lights, you can update. Okay, this is a CIE 1931 chromaticity diagram. You notice how you have an X and a Y on the chart. Well, since firmware 2.5, you can pick a color, any color in the chart, by specifying an X and a Y coordinate. So your X and Y coordinates go from 0 to 0.8, 0.9. Anything outside of this exists, but your eye, you can't see it. So yeah, you can specify any color in here that you want based on X, Y coordinates. select one set of XY coordinates, or one color, as color A, and another second set of XY coordinates as color B, and then you can have the light automatically go from color A to color B. And it can do it in different ways. It can go through the white point in the middle, it can go around the white point underneath, or it can go above the white point. Anyway, I'd have to go back to that chart, but if you look at that color chart again, with the white point in the middle, it means you can select color on the chart over here, color on the chart over here, and the light will automatically fade between one or the other. It's an effect. It's something that I don't see really being used that much in cinematography, but I do see it maybe being used in theatrical applications, for stage lighting, things like that. It's pretty cool anyway.
Can you do time as well?
Sorry?
The time is...
Yeah, the time it takes to, yeah. I kind of imagine a bunch of geeks in ARRI's lab developing the firmware, thinking, this would be fun, let's do this. At least that's what I would do if I was them. You know, when you've got a little computer in the light, then you can do all kinds of fun stuff. So firmware 2, this is the previous firmware update. So all kinds of gels came in. Low end mode. Basically, because cameras these days are getting more and more sensitive in lower and lower light levels, you don't always need to blast your light at 100%. Sometimes that's just too much light. It depends on what you're shooting, what the style is, what other lighting sources you're having to match with. And sometimes with LED panels, when you dim them down to like that zone between 1% and maybe 15%, in some cases there's not so many steps, you know, at that low end. So it's a really small move of the knob to go from 1 to 15, but you want to be somewhere in there. Well, there's a low end mode, which gives you more control or more movement on the intensity knob in that low area, that low light zone. That's useful when you're dealing with low light situations where you need to keep everything dim. Like, let's say you're shooting a candlelit dinner, and there's a couple at a table, and there's candles on, and you need to expose those candles correctly. Well, you're not going to blast that scene with light, and then if you expose to that, your candles, you don't see them. You know, so you're going to maybe fill in, add some soft fill, whatever, but you need to keep your levels down at the similar level to the candle light. That's where you'd use low end mode. And low end mode with accurate correlated color temperature as well. So yeah, if you wanted to match candlelight, you'd be able to do it very well with these lights. This brings me to another thing which I mentioned in the break to a few people, but dimming curves. So again, if you think about how the light changes its intensity from 0 to 100%, it could do that linearly. So you'd have a linear transition from 0 to 100, or the way the light dims from 0 to 100 or 100 to 0, you can actually plot a curve. So there's 4 curves. There's logarithmic, there's linear, there's 2 others. So that allows you to dial in a specific dimming behavior for specific applications. And then there's something called ARRI, which provides your normal DMX 512 protocol, well, and remote device management, but instead of being over a DMX network, it's over a normal Ethernet network protocol. So that's one way that you can use your your Ethernet port on the light. Is this with ARRI? So it gives you your DMX control but over Ethernet networking protocols. So that's pretty cool. And the other thing I want to mention that we don't have yet, as far as I know, actually it's not shipping yet. But again, this was announced at IBC in Amsterdam. It's a SkyPanel remote. So this little guy comes with a 5-meter USB cable. It plugs into the USB of your light, which is where here. And it's basically a solution for if you had a light. Okay, this one's pretty high, but I could at least stand on a chair and reach it. But in some cases in studio or whatever, you might have your light way up high even on a stand. And instead of getting a ladder, every time you want to make some adjustment, this is a really good accessory. It even has a magnetic fastener, so you can just, it sticks on the stand, and it gives you your full control panel and controls that are normally on the back of the light on a little remote. So yeah, for lights that are mounted very high up or whatever, you can have a control panel down that's easy to tweak. And again, this could be combined with the slave master mode as well. So if you had 6 lights and they were all connected by a DMX cable, and you had this controller on your master and the others were slaves to it, then you'd have control over all 6 lights from one of these controllers.
All of them? Only one?
As long as, well, no, you'd have control over multiple lights if they're in slave master mode, and if this one is connected to the master.
And how we control it?
With this,
I know, if it's high or it's...
well, this is the thing. This is on a
Attach it
cable.
to the light.
Yeah, it's USB. So it plugs into the light USB port, and then it's on a 5-meter cable. So if this was up very high, the controller can still be at, at a level where you can reach it. So that's the remote.
So I will use it in all the cases.
Yeah, no, it's very useful. I mean, it will only control the light that it's connected to, so it's not like a remote that will control, a whole range of lights. It will just control whatever one it's connected to, and it will control others if they are slaves to that. In using the slave master mode. But if you want more, sophisticated control over a whole network of lights, then you need to be looking at a DMX control solution. Yeah, and it's the standard DMX protocol, so any DMX controller will work with these lights. So.
In that master and the slave one, can you change it between the presets?
Everything that you can do on the master controller up here will automatically follow on
Even the presets?
the gels. Yeah. So if you change the gel on the master, any other lights that are slave to it
No,
will.
it has a preset, you can save preset on it.
Ah, I see what you mean. If you saved some custom preset.
Can you change that?
There are some presets here
Yeah.
where you can preset
Yeah.
There are.
And you can recall it again, right?
Sorry?
You can recall it?
Yeah, you can call it.
But if you have presets, custom presets on one light,
Mm-hmm.
and that is your master light, and you have some others connected to it which are slaves,
Mm-hmm.
but they don't necessarily have the same preset,
Yeah.
would they follow?
Yeah, that I have to check.
It's a good question.
Yeah.
I'm glad you asked that because it's an interesting question. I don't know the answer to that one.
But maybe you can reset them before starting. Can you reset it?
I can definitely find out. I can find out the answer to that. I can email somebody who knows and find out. But yeah, that's interesting. I've not thought about that situation before.
I have a question for the Ethernet, when you connect it to a router. Shut up. When you connect it to the Ethernet, and I don't know, not that old. But, okay, the device, they can see each other on the Internet, they have a signed IP address.
Okay, see, this is something that I don't know the ins and
My
outs of.
idea is the way how we're playing with the smart TVs and the way how you can see the other devices on the Ethernet through the router. Can you see the lights on through
If
the
it
router?
was a no, because I think it has to be a dedicated network. I don't think it can piggyback off. I don't know this for 100%.
Yeah.
So
we
you're
can
talking
just
about
do
using a normal
But
network
if you
switch.
If you have the application inside of your
Yeah,
phone, you can control different devices and you can see them. You don't have to move from the place. Sometimes
Yeah,
it's
yeah.
normally actually we have a control desk, you know, control desk.
Through DMX.
Yeah, through DMX we have. So these lights, because we have a DMX splitters. End of the day, the lights we can connect to the DMX. Sorry, the Ethernet. It will come to the splitter and the networking switch as well. But all the lights, because in the larger studios, we use not really like we are doing in Kuwait now. Every light have like an Ethernet cable. So it's coming to the DMX splitter, and from DMX to the control desk is a DMX, but other is dedicated Ethernet. It has an IP address for each light, so you can see whether this is because in a interface you can see it's a red or a green, so you can easily find out.
So you should be able to slave as many as you normally be able to use DMX for.
In this one risk is panel, you can control at least 30 lights.
Oh, okay.
30 lights. It's a mixture of not only SkyPanel plus our own like L series as well. So like LED series which is L7, L5, L10 plus SkyPanels. Yeah.
Hi. I'm sorry. That's what we've finished basically. So yeah, that's all I've got to present, but really it's just now, if you want to come up and, it's 5 now already, but if you want to come up and get hands-on, if you have any questions, but yeah, come up and get hands-on. They're actually really simple to use. How heavy? Well, you can come lift it if you want.
Yeah.